Hello, my name is Helen Durand, and I will be presenting our work on control system cyberattack resilience and discoverability for nonlinear systems with changing dynamics. Our motivation for considering changing dynamics in the context of cyberattack resilience stems from concerns with regard to autonomy in the face of variation over time. Data-driven components of controllers allow such systems to adapt to changing environments. But there have been concerns regarding verifying the safety of such systems online as the data-driven components learn and change over time. One type of control law that we can consider is one that incorporates a data-driven model in the control formulation to account for changing process dynamics over time, and therefore to allow the controller to update the dynamic model that it uses as the process dynamics change to account for those changes. Lyapunov-based economic model predictive control, or LEMPC, is a type of advanced control framework that is model-based and therefore can allow for these types of updates to account for variation over time. We've previously looked at developing an LEMPC that is able to handle online model updates and provided the theoretical conditions that would be required for this. However, when cyberattacks could occur on an LEMPC designed to handle model updates in this way, new challenges can arise, in particular that it can be difficult to distinguish between the actual dynamics changes and a sensor measurement cyberattack. And so in this talk, what we'll be looking at is first presenting the type of LEMPC formulation that is able to guarantee stability in the presence of model updates, but the absence of cyberattacks. And then we'll look at how to update a cyberattack detection strategy in order to be able to handle, in the context of LEMPC, both cyberattacks as well as changes in the underlying dynamics. In the following developments, we consider the class of nonlinear systems shown here. This is a general class of nonlinear systems with X bar AI as the state, U bar I as the manipulated input, and WI as the disturbance. The disturbance is considered to be bounded, as are the inputs and the states. We parameterize the different models that can occur over time with the subscript I. This means that the first dynamic model is used when I is equal to 1, and then when the dynamics change, I will be set equal to 2, and when they change again to 3, and so forth. We assume that the system is stabilizable in the sense that there exists an explicit stabilizing control law that can render the origin or steady state asymptotically stable, in the sense that there exists a Lyapunov function for which the time derivative is negative along the closed-loop state trajectories under the control law. For each of the different process models, we define a stability region, omega rho I, which is a level set of each Lyapunov function where the state constraints are met. The second set of systems we consider are those describing the empirical or data-driven models that will be used by the controller, which are characterized here. The nonlinear empirical system is also considered to be stabilizable in the sense that there exists an explicit stabilizing control law, HNLQ, for the qth data-driven model that renders the origin or steady state of the empirical system asymptotically stable, such that there exists a Lyapunov function v hat q, which decreases along the closed-loop trajectories of the empirical system under HNLQ for all states in a neighborhood DNLQ of the origin of the empirical model. We define a region omega rho hat safe q within DNLQ as a level set of v hat q in DNLQ where the state constraints are met. We also define a subset, omega rho hat q, of this region, omega rho hat safe q. We consider that M sets of measurements are continuously available. There is measurement noise, but it's bounded. And in addition, a deterministic observer is assumed to exist for each of the M sets of measurements with the form shown here. For this observer, we make some assumptions, including that there exists a time after which the estimation error is lower than a certain bound. With these models defined, we can now present the general formulation of the Lyapunov-based EMPC, or LEMPC. This is a two-mode control formulation. The mode 1 constraint is highlighted here in red, and it requires that the state predictions be maintained with an omega rho hat E1. Under sufficient conditions, this constraint guarantees that the closed-loop state is maintained in omega rho hat 1. This Mode 1 formulation of LEMPC is always feasible. The explicit stabilizing or Lyapunov-based controller HNL1 implemented in sample and hold is a feasible solution at every sampling time. This formulation also has a level of robustness to disturbances or plant model mismatch. The second mode of operation of LEMPC is shown on this slide, with the Mode 2 constraint or contractive constraint highlighted in blue. This constraint forces the LEMPC to compute control actions that decrease the Lyapunov function and could decrease it to a neighborhood of the steady state. The prior work described guarantees for LEMPC that with a data-driven model, closed-loop stability and recursive feasibility can be obtained. Here, to consider anomaly handling for LEMPC with safety guarantees in the case that the underlying process dynamics can change, making the empirical model also change, we allow the empirical model used in the LEMPC to be updated over time. We note that the closed-loop stability and feasibility guarantees obtained in the case that the model is not updated rely on the accuracy of the empirical model. Changes in the underlying process dynamics may warrant online model updates, but also could lead to more significant plant model mismatch at certain points in time, with the potential that the closed-loop state could leave the stability region. Therefore, to handle the underlying dynamics changes, the LEMPC for anomaly handling is designed to maintain the closed-loop state in omega rho hat Q, which is a subset of omega rho hat safe Q. This ensures that when the closed-loop state at x of tk leaves omega rho hat Q due to a process dynamics change, there is still time before it leaves omega rho hat safe Q. This leads to the following implementation strategy. The system is operated under LEMPC until x of tk is no longer within omega rho hat Q. At that point, it is detected that the plant model mismatch has become large enough to potentially compromise stability. In addition, this detection mechanism of seeing that x of tk has left omega rho hat Q is used to indicate that there has been a change in the process dynamics. Via the implementation strategy described, we are able to develop conditions under which closed-loop stability is maintained even in the presence of the changes in the underlying process dynamics. However, those results do assume that the state measurements are accurate. One of the potential sources of inaccurate state measurements is an attack on the control system sensors, which could occur to impact safety or performance. These attacks could be difficult to detect. The manner in which they would occur is shown in this figure, where we see that a typical control loop could be broken in the sense that a controller no longer receives a measurement from a sensor and instead receives a false state measurement. If some type of false state measurement was injected into an LEMPC, it could be difficult to tell the difference between the cyberattack and the change in the process dynamics. In terms of methods in the case that we have no changes in the process dynamics, we have previously developed 3 different concepts for utilizing LEMPC to attempt to detect attacks and to handle them. These have included an LEMPC with random control law modifications to probe for cyberattacks, an LEMPC that uses state feedback as well as state predictions for detecting the attack, and an output feedback LEMPC that uses redundant state estimators to detect attacks. Here, to demonstrate one of the detection strategies, we show the output feedback LEMPC formulation. The formulation is a lot like the LEMPC design shown earlier that incorporated empirical models, except that it uses a state estimate rather than a state measurement. We can then look at the properties of our state estimator. Based on the properties of the state estimator, in which we assumed that there is a bound on the difference between the state estimate and the actual value of the state, we can obtain that if we have a number of redundant state estimators with this property, the difference between the estimates given by any two of these estimators should be bounded when there is no attack. This suggests an attack detection methodology, in which the difference between two estimators is checked at every sampling time. When there is a difference between those estimators larger than the bound that should be there, we can flag that as a potential cyber attack. So that provided an example of a way that LEMPC can be integrated with attack detection strategies in order to be able to guarantee safety in the presence of attacks if there are no changes in the process dynamics. However, some of our methods for integrating attack detection with LEMPC have relied on state predictions as well as state estimates. Both of these are model-based. What this means is that when the dynamics change, that makes the models that are used in predicting or estimating less accurate. Similarly, when a cyber attack on the sensors occurs, the state estimates or the state predictions will also appear to be less accurate. This means that either a dynamics change or a cyber attack could cause the cyber attack threshold used in detecting whether an attack has occurred in one of the detection strategies to be breached. In addition, either a dynamics change or a cyber attack could cause the closed-loop state to leave the region omega rho Q. In order to handle this, we developed a two-stage detection strategy based on the state prediction and estimate methods to be able to prevent the closed-loop state from leaving omega rho safe Q before a certain amount of time passes. In the two-stage detection strategy, if the closed-loop state leaves omega rho Q or if an initial detection threshold is reached, we both reset the detection threshold as well as prepare to re-identify the model. This allows us to handle the ambiguity in whether the first threshold breach is due to an attack or a model change. With this updated implementation strategy, we are now able, in the case that we use state predictions as part of our detection strategy, to develop sufficient conditions which maintain the closed-loop state within omega rho safe Q for at least one sampling period after either an undetected attack or a model change. In the case that we use the state estimation-based attack detection technique integrated with LEMPC, we are able, with the updated implementation strategy, to develop sufficient conditions which maintain the closed-loop state within omega rho safe Q for all times for an undetected attack or a model change. To demonstrate the proposed methodology, we here show a chemical process example. In this example, a continuous stirred tank reactor with a second-order A to B reaction is utilized. The control objective is to optimize the process economics while maintaining the closed-loop state in omega rho Q safe. We consider a Lyapunov-based controller and quadratic Lyapunov function. The LEMPC in this case receives full state feedback, but there is process noise, meaning that the state feedback does not provide a perfect state measurement. And in addition, we consider as the redundant estimator a high-gain observer that estimates the reactant concentration from temperature measurements. The observer design is shown here. The first threshold on the norm of the difference between the state estimate and measurement was set to 0.9520, and the second threshold was set to 1. After 30 minutes of operation, we change the value of K0, which is used in the reaction rate law. This corresponds to the change in the underlying dynamics. The state space plot for 2 hours of operation is shown here, where we see that even after the change in K0, the closed-loop state never left omega rho safe Q or omega rho Q. In conclusion, this work developed a control and detection strategy that can handle both changing process dynamics as well as cyber attacks on the process sensors. It does not require all cyber attacks and dynamics changes to be definitively distinguished. The chemical process example demonstrated the concept that it could be difficult for a pre-designed detection algorithm for cyber attacks or pre-designed detection algorithm for model changes to necessarily distinguish between those two. We would like to thank the Air Force Office of Scientific Research, National Science Foundation, and Wayne State University for their financial support.